Hello everyone, welcome to Civil Galaxy. In today's session, we shall see how to analyze a frame with the help of Kanis method. So for that, I have considered a problem over here where this frame is subjected to an uniformly varying load of 24 kilonewton per meter, and at point B, it is subjected to a lateral load of 100 kilonewton. So from previous classes, we have learned that whenever a frame is subjected to an asymmetric loading, it is subjected for the lateral sway. So while analyzing this particular frame, we need to consider the lateral sway component also into the consideration. So from previous classes, we have learned in Kanis method, the first step will be to calculate the fixed end moments. To calculate the fixed end moments, that is FEM. So if you observe the frame over here, A to B and D to C, there is no external loading. So fixed moment from A to B and fixed moment from B to A, also fixed moment from C to D and fixed moment from D to C will be equal to 0. So now if we take the span BC over here, the fixed moment from B to C, since it is carrying an uniformly varying load of intensity 24 kilonewton per meter, the formula here is WL square upon 30. Since we are coming from left to right, it will be negative. So here minus the load they have given here, it is 24. So 24 into span, we know it is 6 meters. So 6 square upon 30. So this will be equal to a value of minus 28.8 kilonewton meters. Similarly, if we calculate from right to left, the fixed end moment from C to B will be equal to, now it will be positive because we are coming from right to left. So plus WL square upon 20 for uniformly varying load. So this will be equal to plus 24 into span, we know 6 square upon 20. So this fetches a value of plus 43.2 kilonewton meters. So after calculating the fixed end moments, the second step in Kanis method will be to calculate the relative stiffness, that is to calculate the relative stiffness and rotation contributions. So to calculate the relative stiffness and rotation contributions, we have learned from our previous classes that we need to consider the joints, and for that particular joints we need to consider the members, and then for that particular member we need to calculate the relative stiffness, which is represented by K, and we will consider the summation of the total stiffness. Then we will calculate the rotation contributions, which is represented by U is equal to minus half into K upon sigma K. So this is the formula we need to use for calculation of rotation contributions. So if we observe the joints over here, we are having two joints over here, that is B and C. So we are having two joints, that is B as well as C. So if you see here at a joint B, we are having B to A and B to C. So we are having two members. So B to A as well as B to C. Similarly, For joint C, we are having C to B and C to D. So we are having two members over here, that is C to B as well as C to D. So now if we need to find out the relative stiffness, we know whenever we need to find out the relative stiffness, we need to consider the far end conditions. So for this member, B is the near end and A is the far end. And since A is the far end here, which is fixed in nature, so the stiffness will be equal to I upon L. So I value they have given here, that is I itself, I upon the total length over here is 4 meters. So this gives a value of 0.25 I. So now if we take the member B to C, B is the near end and C is the far end, and since C is an intermediate support over here, intermediate support also is considered as an fixed support, so the stiffness will be equal to I upon L. So the value of I they have provided here for member BC, which is 1.5 I. So 1.5 I upon the total span here is 6 meters, which gives a value of again 0.25 I. So just highlight over here, so it will be easy. So for member BA, the relative stiffness is 0.25 I, and for member BC also the relative stiffness is 0.25 I. Similarly for member CB, now C is the near end and B is the far end over here, and B is an intermediate support. For intermediate support, the relative stiffness is taken as I upon L. So I value they have provided, it is 1.5 I upon the total span is 6 meters. So this gives a value of again 0.25 I. So now lastly for member C to D, C is the near end and D is the far end over here. Since the far end is fixed in nature here, the stiffness will be equal to I upon L. So I value they have provided, that is I upon 4, which will be equal to 0.25 I. So now we have to consider the total stiffness of the joint B over here. So 0.25 plus 0.25 gives a value of 0.5 I. Here also for joint C, the total stiffness will be 0.5 I. So now if we just put the value over here, that is K upon sigma K, the rotation contributions for member BA, we are having a value of minus 0.25, and for member BC it is minus 0.25. For member CB also it is minus 0.25, and for span CD also it is minus 0.25. So after calculating the rotation contributions, if we observe in this frame over here, since it is subjected to a lateral load and an asymmetric loading over here for span BC, this particular frame is subjected for a lateral sway. So whenever we are considering the lateral sway component into consideration, we need to calculate one more value, that is the displacement factors. Along with the rotation contributions, we need to calculate the displacement factor as well. So to calculate the displacement factor, we need to consider again one more table over here. So if you observe over here, it is having a single bay and a single story. So first will be story, and for that particular story we need to consider the vertical members. So it will be vertical members, and for this particular vertical members we need to find out the relative stiffness, which is represented by K, and the total stiffness, that is sigma K. Also we need to calculate the displacement factors, which is given by U double dash is equal to minus 1.5 into K upon sigma K. So this is the formula. So now if we see over here, we know that it is having only one story over here. So story is 1, and the vertical members we have, that is B to A and C to D. So vertical members will be B to A and C to D. So the relative stiffness, we know B is the near end and A is the far end. Since A is the far end here and it is fixed in nature, so the stiffness will be equal to I upon L. So I value is provided, it is I itself, and the total length here is 4 meters, which will be equal to 0.25 I. So similarly for C to D, since C is the near end and D is the far end, and the far end is fixed in nature here, so we are having the value of I upon L. So this will be I by 4. So this gives a value of 0.25 I. So now if we take the summation of these two, this will be equal to 0.5 I. So if we just put the value over here, that is minus 1.5 into K upon sigma K, we are getting a value of minus 0.75 for vertical member BA, and for vertical member CD also we are having a value of minus 0.75. So the next step will be to calculate the rotation contributions. So the step 3 will be to calculate the rotation contributions through the iteration process. Through the iteration process. And to carry out this iteration process, first we need to carry out or construct a table which is called as a Kanis table. So if we observe over here, the rotation contributions are calculated only for the intermediate supports and not for the end supports. So what we have taken here is, for the intermediate support we have replaced the joints with the help of boxes over here. So first we will represent the fixed end moment whatever we have calculated in the first step. So the fixed end moment from A to B, it was 0. Similarly from B to A, it was also 0. So from B to C, the fixed end moment, we have got a value of minus 28.8 kilonewton per meter. Sorry, 28.8 kilonewton meter. So I am taking only the values here and not the unit. And from span C to D, we have got a value of plus 43.2 kilonewton meter. Similarly, the fixed end moment from C to D was 0 and from D to C also it was 0. So now what we have to do, inside this small box over here, we have to take the summation of the fixed end moment about this particular joint over here. So this is 0 from B to A and from B to C it is minus 28.8. So if we take the summation of these two, we are getting a value of minus 28.8 kilonewton meters. Similarly, for joint C over here, if we take the summation, it will be plus 43.2 kilonewton meters. So now, the next step, what we have to write here is, whatever the rotation factors we have calculated in the second step, we have to write here in this box over here. So the rotation factor from B to A, for member B to A, we had got a value of minus 0.25, and here also from B to C we have got a value of minus 0.25. So from C to B also we had got a value of minus 0.25, and from C to D we had a value of minus 0.25, which we have got in the second step. Apart from calculating the rotation factors, we have also calculated the displacement factor, since this particular frame is subjected for the lateral sway. So for member B to A, the vertical member B to A, we had got a value of minus 0.75. Similarly, for span C to D, we had got the displacement factor value as minus 0.75. So now, if we calculate the rotation contributions, so if we need to calculate the rotation contributions, which is represented by M dash AB over here, it is M dash BA. Here it will be M dash BC. This will be M dash CB. Here it is M dash C to D. Here it is M dash D to C. So as we know that the rotation contribution is calculated only for the intermediate supports and not for the end supports. So the rotation contributions about the end supports, that is M dash AB, will be equal to 0, and also M dash DC will be equal to 0 over here. Apart from calculating the rotation contributions, we are having a rotation. This one is the displacement contributions, which is represented by M double dash, that is from B to A. Also here it is M double dash C to D. So we need to calculate the displacement contributions also. So if we go on carrying the iteration process, so let us consider the first cycle. So for first cycle, if we need to calculate the rotation contributions, from previous classes we know that the rotation contribution is given by M dash is equal to U into summation of fixed end moments plus summation of far end rotation contributions. This is the formula we are going to use. So now if we just take this value over here, that is M dash BA. See, if we observe over here at joint B, the rotation factor value from B to A and the rotation factor value from B to C are identical. So we can calculate the rotation contributions, that is M dash BA and M dash BC value will be identical and same. So we can calculate at a time. So M dash BA will be equal to M dash BC over here, which will be equal to, see here, the value of U, that is the rotation factor value we have got, that is minus 0.25, and the summation of fixed end moment value we have got here, that is minus 28.8, plus summation of far end rotation contributions. So now if you want to calculate the far end rotation contributions, which is the far end rotation contribution over here for this joint over here, see M dash BA, this will be the far end rotation contributions 1. Also M dash CB, so this will be the far end rotation contributions over here. Also we are having one more, that is M double dash BA, that is the displacement contributions. So this is also the far end rotation contribution we have to consider while calculating. So we are having 3 values over here. So now if we take plus the far end rotation contributions, that is M dash AB, we know it is already 0, and M double dash BA we don't know, we need to calculate, plus M dash CB we don't know, we need to calculate. So for the first cycle it will be equal to 0 over here. So we are having a value of, so we will have a value of, that is 7.2 kilonewton meters. So this is the value 7.2 kilonewton meters. So this value we will write over here, that is M dash BA, we are having a value of 7.2 over here. Here also it is 7.2. So now we need to calculate the this rotation contribution for M dash CB, which will be equal to M dash CD, since the rotation factor value are identical, it is minus 0.25 and minus 0.25, which will be equal to the rotation contribution, the rotation factor value we know, that is minus 0.25 into summation of fixed end moment. So the summation of fixed end moment over here is how much? Plus 43.2 plus summation of far end rotation contribution. Far end rotation contribution here, this one. See, for this joint over here, which is the far end rotation contribution over here, m dash dc and m double dash cd, also m dash bc is the far end rotation contributions. So now see here. So the far end rotation contributions m dash dc is 0 and m double dash cd we don't know, we need to calculate. So for first cycle it will be 0, and the far end rotation contributions, that is m dash bc, we are having a new value over here, that is 7.2, that is new iteration value, which is 7.2. So if we just calculate the value over here, we are having a value of minus 12.6 kilonewton meter. This is the value. So now this value we will provide over here, minus 12.6, here it also it is minus 12.6. So now apart from calculating the rotation contributions, we also we need to calculate the displacement contributions. So the displacement contributions is given by the value u double dash. Since this frame is carrying a lateral loading, it is having a formula of the story shear multiplied by the height of the story divided by 3 into summation of that is m double dash t, that is the displacement contributions about the top plus the displacement contributions about the bottom. This is the formula. So now if we want to calculate this story shear over here, which is SRHS, the story shear is 100 kilonewton, we know it's given in the problem, and the height of the shear, height of the story, it is 4 meters divided by 3. So just apply this value over here. So u double dash, we know the value, it is minus 0.75. So it is minus 0.75. So this value if you provide over here, that is story shear is 100 multiplied by the height of the story, that is 4 meters divided by 3 into, if we just observe over here, m double dash t at the top over here, that is 7.2. So we are getting a value of 7.2 over here. So it is 7.2 plus at the bottom it is 0. So at the bottom it is 0 over here. Also at the top, that is summation of the displacement contributions about the top and the summation of the displacement contributions about the bottom. About the bottom here, if you see, it is 0 plus 0 over here. At the top we are having here 7.2 and here one more value is minus 12.6. So if we just calculate these values, we are having a value of, that is minus 95.95 minus 95.95 kilonewton meter. So this is the value. So this value we will just provide over here, that is minus 95.95. So the same value here also we will write it. So minus 95.95. So this is the first cycle. So now similarly we need to go on calculating the values until we are getting the similar values over here. So for that what we will do here is, all the values, that is the rotation factor and the summation of fixed end moment remains same. Only the far end rotation contributions keep on changing. So we will just change the values over here. So here also, okay, see here. So for now m dash BA over here, m dash BA, the summation of fixed end moment up to here, the value remains same. So now if we need to calculate the summation of far end rotation contributions, the value changes over here. That is 0, first one is 0 over here for the far end rotation contributions. Next we are having a new value over here, that is minus 12.6. Also we are having a new value over here, that is minus 95.95. So we are having a value of 34.33 kilonewton meters. So this value, just put this value over here, that is 34.33, 34.33. So now similarly just add the values over here. 34.2 is the summation of fixed end moment. About this point we are having a value of how much? Now new value, that is 34.33 plus 0, because about the far end rotation contributions here is 0, and here we are having a new value, that is minus 95.95. So we are having a value of now, that is 4.605 kilonewton meters. So this value will provide over here, that is plus 4.605, here also plus 4.605. So now similarly here if we add the new value over here, summation of the displacement contributions about the top over here, we are having the new value, that is 34.33 plus a new value over here, that is plus 4.605. So if we calculate, we are having a value of here minus 129.20, minus 129.20 kilonewton meters. So this is the value over here. So just put this value over here, that is minus 129.20. So here also minus 129.20 kilonewton meters. So this was the second cycle. So now going for the third cycle. So going for the third cycle, only the rotation contributions, the far end rotation contribution changes. So this value will change over here for the displacement contributions. So now if you observe over here, plus for m dash BA, now the far end rotation contributions, first one is 0 over here, and here we are having the new value, that is plus 4.605 and minus a new value over here, it is 129.20. So if we calculate this one, we are having a value of 38.35 kilonewton meter. So this value will write over here 38.35, here also 38.35, and now if you want to calculate the rotation contributions for m dash CB and m dash CD, so here we are having a new iteration value, that is plus 38.35 plus 0 about this value over here, and we are having a new value, that is minus 129.20. So we are having a value of, that is 11.91 kilonewton meters. So this value will provide over here 11.91, and sorry, not here, this is here. plus 11.91 plus 11.91. So now if you want to calculate the displacement contributions, about the top here, the value here if you see, that is 38.35, a new value. Also here it is having a value of plus 11.91, and about the bottom it is 0 and it is 0. So we are getting a value of minus 137.70 kilonewton meters. So this value will provide over here minus 137.70. So here also minus 137.70. So next will be the fourth cycle. So next will be the fourth cycle. So for fourth cycle also, the far end rotation contributions changes. So see here. So this is the fourth cycle. So here the far end rotation contributions, now we are having a new value over here, that is plus 11.91, and also we are having a new value that is minus 137.70, and it is plus 0 for m dash AB over here. So we are having a value of, that is minus 38 plus 38.64 kilonewton meter. This is the value. So this value will provide over here 38.64 here, 38.64 here also it is 38.64. So here 43.2 is the summation of fixed end moment. The far end rotation contribution here we are having a new iteration value 38.64 and minus 137.70, this one value here, and the far end rotation contributions about m dash DC is 0. So we are having a value of 13.96 plus 13.96 kilonewton meters. So 13.96, it is plus 13.96, here also plus 13.96. So now if you want to calculate the displacement contributions, so here we are having a value that is 38.64 plus 13.96, and the summation of rotation contributions about the displacement contributions about the end is 0 over here. So this we are getting a value of minus 139.45. So minus 139.45 kilonewton meters. So this value will provide over here minus 139.45. Here also it is minus 139.45. So if we observe over here the values about m dash BA and m dash BC, it is almost similar over here, but in this case m dash CB and m dash CD, it is still not identical. Here also 137.7, 139.45. So we shall see for another one cycle, probably we can get an identical values. So going for the fifth cycle, so going for the fifth cycle, so here we are having a new value over here, that is plus 13.96, and here a new value, that is minus 139.45 plus 0. About this point over here, we are having a value of 38.57 plus 38.57 kilonewton meters. So this value will provide over here 38.57, here also 38.57. So here the new iteration value we are having, that is plus 38.57 and minus this one here 139.45 plus 0. About this point is 0 over here. So we are having a value of 14.42 kilonewton meters. So this value 14.42. So plus 14.42, here also it is plus 14.42. And next, if we take the displacement contributions value over here, we are having a new value over here, that is plus 38.57 plus 14.42. We are having a value of minus 139.74 minus 139.74 kilonewton meters. So this value minus 139.74, here also minus 139.74. So if you observe over here, almost the values are similar over here now. So here also, so this we can consider as the final value for the calculation of the final end moments. So this value here, so here also it is approximately almost similar, 14 and 13.96 we can round it off for 14. So this value over here we can consider it for the final calculation of the final end moments. So now going for the last step, that is step 4, calculation of the final end moments. So if we just go on calculating the final end moments in the step 4, step 4 will be to calculate the final end moments. So to calculate the final end moments, that is from A to B, we know the formula, fixed end moment from A to B plus 2 times the rotation contribution about the near end and 1 time the rotation contribution about the far end. Also for A to B, we are having a displacement contribution over here. So it will be M double dash BA. So now if we calculate and just put the values over here, we know the fixed end moment from A to B we have taken here it as 0, and also what is M dash AB here, that is the near end rotation contributions. So this one also is 0 over here, plus the rotation contribution about the far end M dash BA, the value we have got here, that is 38.57 plus M double dash BA, we have got a value here, how much, minus 139.74. So the final end moment from A to B, we are having a value of minus 101.17 kilonewton meter. This is the value. So similarly for MBA, that is final end moment from B to A, that is fixed end moment from B to A plus 2 times the rotation contribution about the near end plus 1 time the rotation contribution about the far end plus the displacement contributions M double dash B A. So now MF BA, this is 0 because we are not having any loading. The fixed end moment from B to A already we have calculated, that is 0 plus 2 times the rotation contribution about the near end. Now M dash BA, how much it is? 2 into 38.57. This value is 0. And M double dash BA here we have calculated, that is minus 139.74. So MBA will be having a value of minus 62.6 kilonewton meter. This is the value over here. Now if you want to calculate from B to C, the final end moment from B to C will be equal to fixed end moment from B to C plus 2 times the rotation contribution about the near end plus 1 time the rotation contribution about the far end. See here, we have calculated the displacement contributions only for the vertical members and not for the horizontal members. So we need not apply the displacement contribution value over here. So just apply the value over here. The final end moment will be equal to, I have calculated, I'll just write the values over here. So B to C we are having a value of 62.76 kilonewton meters. Similarly, final end moment from C to B we are having a value of 110.61 kilonewton meters. And the fixed end moment from C to D, fixed end moment from C to D, we are getting a value of minus 110.9 kilonewton meters. And fixed end moment from D to C, fixed end moment from D to C, we have got a value of minus 125.32 kilonewton meters. So if you just observe over here, from B to A it is minus 62.6 and from B to C it is 62.76, almost equal. So this is, we can say that the frame is in equilibrium and the calculations are correct over here. Similarly, from C to B it is 110.61, here also it is 110.61 kilonewton meters. So this is how we calculate or analyze a frame which is subjected to sway analysis with the help of Kanis method. So similarly we shall see few more problems in the next coming classes. Thank you.